All right, guys. Good morning, good afternoon, good evening, wherever you are joining from. This is Uncle Sam, and we are back again for another moment of transitioning beyond knowledge to gain understanding. I'm so excited to have you here. This is our day 9 of going live on YouTube to discuss concepts related to mathematics, unlike the way you've ever had it before, basing on simplifying concepts in a way that is very, very interactive and more like storytelling. So it's going to be very, very interesting, just like it always is. So for today's class, we're going to be looking at this concept. We've been talking about logarithm since Friday last week, and we're still continuing with that because I want you to have a solid understanding of this concept and in a way that is going to stick to your head. So we're going to be observing equations and substitutions in logarithm. But before we get into that, first of all, I'm going to review a question that I solved in the previous class on Wednesday. Like I said, I go live on YouTube 3 times in a week, Monday, Wednesdays, and Friday by 4 p.m. West African time, that is Nigerian time, okay? And you can always catch me when I go live by 4 p.m. So I'm going to be reviewing a question to begin with for today. There's a question that I solved in the previous class that there was a bit of error, so I want to correct that right about now. So what is it that I'm talking about? Well, we solved a problem that had to do with something like this: log 32 base 0.25. And we're asked to simplify this particular word expression. To simplify, yeah, because it's still simplification. And one of the things that we did here was to employ the concept of change of base. And after employing the concept of change of base, I gave you another approach that you could have used to solve this particular problem. So the one I want to address is the concept of change of base. When you want to solve a problem like this now, you see that both the log and the base, they are dissimilar. They don't have anything in common because the log is a whole number value. The base is a decimal number. So there is no much similarity between them. So one of the things we say that we're going to do, or we employ, one of the rules that we employ under logarithm when we get any kind of challenge in solving problem is to apply the change of base, which is part of the laws of logarithm. So we apply change of base, and this is where I made a bit of error in my calculation, where I told you that the concept of change of base, if I have an expression log a base b and I want to apply change of base, it is not equal to, pay attention, it is not equal to log a bc minus log b bc. No, it's not equal to this. This is wrong. This is actually what I use in solving a problem, and it's actually wrong because I'm not supposed to do that. Welcome, guys. Thank you so much for joining. Thank you. I appreciate you being here. So this apply change of base here, which simply means that the log is going to have its own base, and what the base initially will not have its own base. It is not equal to this. According to the change of base system, this, when you apply the change of base system, is not going to give you the log of a to a new base, which is the new base that we introduced, which is base c, divided by what? The log of the original base now becomes a log, and then the new base that we introduced. This is it. So this expression, applying change of base, will give you this and not this. So take note of that. This is very, very, very important. This is what I want you to pay attention to. So at this point, now that we have examined that this is what this is about, the next thing I'm going to be doing is to use that concept to explore this particular question on the board. So I'm going to clean this up and well, let me just leave it and continue solving here. So applying this change of base system here, well, if I'm applying a change of base, it's left for me to know which new base I want to introduce to solve this problem. You can decide to choose any base of your choice. You can decide to choose base 10 or any other base that you want. So for this particular problem, I want to choose base 10. So I'll write it here. Changing to base 10. Base 10. That is applying change of base to this particular problem. That means changing each of them now to have a base 10. It's not going to be the log of 32 to the base of 10, which I've now what? Applied. Remember, the concept of change of base system simply means that both the log and the base, log and the base, will now become individual logs, and then we'll introduce a new base to them. That is basically what it is about. So at this point now, this is what we're doing now. We're saying that we want to change this original expression, log 32 base 0.25. We want to change it to now become what? A new base will be attached to them. And then the log will now have its own base of 10. And then the original base, which is what? 0.25, will now have its own base. So this is what it means to what? Apply change of base system. Please, it's not subtraction, it's actually what? Division. When you divide what? The original log and divide what? It by the original base, which is now having a new base. That is the basic idea behind this. So when we get to this point now, we simply do simplification. That's what we simply do. Now, what can we do here? Well, we can apply the concept of indices here, which is a base and a power. I can reduce 32 is same thing as 2 to the power of 5. So I can reduce 32 to be 2 to the power of 5. So this is same thing as log of 2 to the power of 5 base 10 divided by, now, is there something I can do to 0.25? Well, it turns out that 0.25, if I change it to fraction, it will give me 25 over 100. And if I reduce it to the lowest term, it's going to give me 1 over 4. And 1 over 4 is same as 4 to the power of minus 1. And I can reduce what? This 4 to be 2 squared, which is same as what? 2 squared, now having a power of what? Negative 1, which came from the inverse of 4. Remember, this 4, I'll switch it up to become what? 2 squared. And then the inverse, this is 1 over, is same as power of negative 1. That is simply what I'm doing here. And then, according to one of the laws of indices, if I have two powers, one inside and one outside, they will both multiply themselves. So this is something as well, 2 raised to the power of 2 times negative 1 will give me what? Negative 2. So this 0.25 can be replaced with 2 raised to the power of what? Negative 2. So this now becomes log of 2 to the power of negative 2 base 10, because we have applied a change of base system. Each of them is now having what? The same base. So when we get to this point now, we now apply another rule of indices, which states that if the log has a power, it's okay to take the power and push it so that it comes at the back or becomes the coefficient of the log. So I'm going to apply that here and here. So if I do that, user, welcome. What is log minus 1? Well, log of 1 at all is equal to 0. Yeah, log of 1 is equal to 0 according to the rule. So I'm going to clean up here so that I will finish it off. I will leave this question and clean here. I'll leave the question, so I'll finish up here. So if I go on to simplify this by applying one of the laws of logarithm, which says that if the log has a power, it's okay to push the power to become the coefficient of the log. So this now becomes 5 log 2 base 10. For this, I've pushed the power here, which I reduced from 32. 32 is something as 2 raised to the power of 5. So I replace 32 with 2 raised to the power of 5. And I now push the power to become the coefficient of the log. It is applicable in logarithm. So this becomes 5 log 2 base 10 divided by, do the same thing here. This log here, which is 2, has a power of negative 2. Push it at the back of the log, it becomes negative 2 log 2 base 10. Now I've got it at the angle that I want. What do I mean by that? You see that at the numerator, I have log 2 base 10, and it's common to both the numerator and the denominator. So they can simply go and cancel out each other. So then what I have remaining is negative 5 over 2, which is same thing as what? Negative 2.5. That is what you have. So that's one of the ways of solving this problem. And after I finish using this change of base system to solve this problem, I give you a trick. That is quite important, that is quite very interesting, that I can actually use to solve this kind of problem without having to go through this change of base system. And that's what I'm going to do now. Minus 1. What is log of minus 1? What is log of minus 1? If you're asking log of minus 1 user, that means the base is actually what? 10. So what you're actually asking here is, what value will I raise to the power of what? Will 10 be raised to the power to give me negative 1? Well, is there such a value, user? Tell me. Is there a number that when you raise it to the power of, let's say we'll have it a variable x, what power will I raise to the power here to give me what? Equals to 1. That's the basic idea. That's the basic idea. So we're going to come back to that. So what I'm going to do now is to use a simplified version to solve this, which I told you guys in the previous class. So if I'm to solve this without involving the change of base system, remember a rule that I told you. If we have that log A raised to the power of B base C, one of the ways I will solve this problem is take the power, which I employed in the last question, and multiply the log. It becomes the coefficient of the log. This is something as B log A base what? C. That's what we have. And so if we got to this point now, it simply means that if the log has a power, it becomes the coefficient. But what if it's the base that has the power? Which is, if I have log A base C raised to the power of B, what do you think is going to become here? Pause and reflect on this and see if there's something you can come up with respect to what we have here. If it was a log, it becomes the coefficient. If it was the base, what I simply said was it's going to be the reciprocal or the inverse of what? Inverse of the power of the base multiplying the log. So this is same thing as what? 1 over B. That's the power of what? The base becoming the coefficient of what? Log A base C. So with that in mind, we can employ it here, because when we simplify this question at first, it gave us that 32 is same thing as what? 2 to the power of 5. And then 0.25, when you reduce it to the lowest term and apply a base of what? 2, is same thing as what? 2 to the power of negative what? 2. 2 to the power of negative 2 is same thing as 1 over 2 squared, which is same thing as 1 over 4. And 1 over 4 is same thing as what? 0.25. So we just converted it to become a fraction and applied indices law to make it to be represented in terms of a base and a power. This is what we have here. So what can we apply here based on this rule? We know that if the log has a power, it can become the coefficient. So this is something as saying 5 log 2 base 2 to the power of negative 2. And I now introduce something that is interesting to you by telling you, oh, it is log exponential. Wow, exponential. Yes, thank you so much. Thank you. Because exponential is used to represent logs that give you like unending decimal numbers. Thank you so much. Thank you so much for that, user. I appreciate that. So at this point now, what we have is this. And then remember what I said here. If it's the base that is having a power, it's going to be what? Coefficient is going to be the inverse or reciprocal of the power of the base multiplying what? The log. So this is something as saying 5 multiplied to 1 over minus 2. This minus 1 over minus 2 is coming from the what? The power of what? The base. Because here the base is having a power of what? Negative 2. So remember, it will now change to become the inverse or the reciprocal of what? The power multiplying to the log or becoming the coefficient. So that is it. This 5 is for what? The log itself, which is what? Log 2 raised to the power of 5. Then this inverse or reciprocal of negative 2 is what we have for the base. Then this multiplied to what? Our log 2 base 2. So we stripped both the log and the base of their power. We stripped them of their individual power and is now multiplying to the log. So we know that this is same as 5 multiplied minus 1 over 2 multiply the log of any number to its base is equal to 1. So this is equal to 1. So what do you do here? You simply multiply. All the numerators will multiply. 5 times minus 1 times 1 is going to give us minus 5. 1 times 2 times 1 is going to give us what? 2. So minus 5 divided by 2 is same as what? Minus 2.5, which is what we got originally when we applied a change of base system. So your choice. If this is applicable, if something like this is applicable, where you're able to reduce your expression into having the same value as in the base, you can actually employ this formula and solve it. So thank you so much. Take a screenshot if you may. I'm going to be exploring now substitution because that's the major focus. I just had to chip this in because I made a mistake in the last live class that we did where I explored this particular question. So now we're going to go into the substitution aspect of logarithm. Quite interesting. So I'm going to clean this up and talk about substitution in logarithm. Now remember that substitution is quite is something that we use a lot in mathematics, and it's quite easy. For example, if I have that 2p minus 3, let's say 3z is equals to 10, and we say where p is equals to 10, find z. Now what I'm going to do here is to substitute the value of what p to become 10. That means anywhere I see p, I'm going to replace it with what? 10. That is what substitution is all about. Sometimes you need to first of all reduce the expression. Sometimes you have to simplify the expression before you can now do the substitution. So in this case, this becomes 2 open bracket, we replace p with 10 minus 3z equals to what? 10. So you see that at this point, this becomes 20 minus 3z equals to 10. It's now looking like a linear equation that we can actually solve without any trouble. So we can decide to add 3z to both sides. It becomes 20 minus 3z plus 3z equals to 10 plus 3z. So if we do that, it's going to give us that this cancels out. It becomes 20 equals to 10 plus 3z. And we can decide to subtract what? 10 from both sides. It becomes 20 minus 10 equals to 10 plus 3z minus 10. This clears up this, and this gives you 20 minus 10 gives you 10 equals to 3z. And then you divide both sides by the coefficient of z. You see that your z equals to what? 10 over 3, or 3 whole number 1 over 3. Now this is substitution playing out in a normal linear equation. So in the same light, when we have expressions in logarithmic form, we can actually do substitution. I think it's just the basic idea, replacing a given unknown variable with something else, or replacing a given number or constant with a variable. That is basically what substitution is all about. Thank you for this. We know we find it makes sense because of your patience and beautiful work teaching. Even with a small audience, you're teaching with great passion. Thank you, Rio. Thank you so much. I'm so happy. I'm so happy that it's making sense to you. Thank you so much. Thank you for joining. And I'm very, very happy that you're having a better understanding of logarithm. Trust me, I am. I appreciate you being here, brother. So what did we do next? Substitution. We're going to start off with equation. Because substitution is it's not really hard. We just need to do the necessary simplification and do the replacement, which is what substitution is all about. I'm going to use the equation to explain that. So look at this equation. Given that x is equals to log 2 and the y is equals to log 3. Y is equals to log 3. Express log cube root of 72 in terms of x and y. That is what we're asked to do. We're asked to express log cube root of 72 in terms of x and y. Now, by looking at this particular question, one thing you will notice is we are asked to express this, the whole of this, in respect to x and y. So it's very clear. We have to do, at some point, we have to do a substitution into this logarithmic expression. But we cannot do that just like this, because first of all, this expression does not have 2. It has log cube root of 72. So obviously, sometimes you don't just substitute in a given expression when it is given. You have to do some basic simplification, and I'm going to take your hand and go through this simplification problem with you, so you see how we simplify before we can now go and perform the substitution reaction. So what can we do first here? First of all, remember that anytime you're given a log and the base is not visible, this is simply log 2, this is simply log 3, this is simply log cube root of 72. One thing you must know there is the base is what? 10. So each of these expressions here have a base of 10. So let us sink in. So we're working with base 10. Now that's all. Now, what is the necessary thing I can do? Well, I can just try simplifying the expression. Let me just do one or two things that I know to be right. So this is something as, if I have log cube root of 72, which is what I was given, this is same thing as saying log 72 raised to the power of 1 over 3. Why? Because cube root is same thing as power of 1/3. That's what it simply means. And remember, I can decide to make the base 10 visible or not. You can decide to make it visible, you can decide to leave it, still the same thing. So here I choose to allow it to still remain invisible. So let's continue. Now, according to one of the laws of logarithm, when the log has a power, it's okay to take the power and it becomes the coefficient of the log. So this is something as what? 1 over 3 log 72. This is what we now have. And at this point, we've not really made any headway because from the question, we are asked to replace this expression to be in terms of x and y. So we've not really made any headway, but we're still in the process. So what can we do here now? Well, since we are working backward, what we are simply going to be looking at here is what will multiply itself to get 72. Since I can only apply the value of x, I can only replace x to be log 2 and y to be log 3. If I have something that shows it, like that means I need to simplify 72 up to a certain level to be working with 2's, log 2's and log 3. That is what I'm trying to achieve. So I'm working backward. How did we get 72? 72 is something as what? 8 times 9. So I can replace this to now be 1 over 3 log into 8 times 9. Yes, I know that 8 times 9 is what will give me 72. Well. Isn't this interesting? Why is it interesting? Because at this point now, I cannot be able to replace this 8 and 9 to be something else. But before I do that, I need to also, first of all, walk backward. Now, according to, we are following the rule, because anything you do and you don't follow the rule is not going to make sense. So stick with me here. Now that I've gotten here to this point now, and I know that if I have this kind of expression, it's multiplication. If I want to walk back to how it was gotten originally, this multiplication will now change to addition. So this is simple as saying 1 over 3, which is the power, which is now the coefficient of the log, that is multiplying all the log. I'll now keep it outside the bracket, and this is something as what? Log of 8 plus the log of what? 9. We're working backward because this is where it's all started according to the basic law of logarithm. If I have addition of the log, it simply means take the base, provided that the base is common, because here the base of each of them is still the base of what? 10. Since the base is common, multiply the log, 8 times 9. So we're working our way backward. That is basically what is happening here. And then when we get to this point now, we can now apply this concept. 1 minute. We can now apply this concept of log 2 and log 3. But how do we apply it? Well, I can do something interesting here. I know that 8 is something as 2 to the power of 3. And I equally know that 9 is something as what? 3 squared. So can I go and replace this value for 8 and 9 with this in this expression? Turns out I can, because I'm not really changing anything. I'm just expressing a given value in another form. So we can go ahead and replace this to now be, remember, 1 over 3 is still outside of the bracket. Then open bracket, you now have what? Your log 2 to the power of 3 instead of what? 8. And remember that the whole goal of this, the reason why I'm going through this route is because of what I'm presented with, the information that I'm giving. I cannot work otherwise. The only information, volume of information that was given is that x, we'll have to replace x with log 2. But there's no log 2 in the given question. So I'm working backward, trying to simplify the concept to see if I can get something related to log 2. And that is what has got me to this point. So we're actually making headway. Then, plus the same thing will happen here. I can go ahead and replace 9 to be 3 squared. So this is the same thing as what? Log 3 squared. This is what I have now. And once I've done this, I can still apply the power law of logarithm, which I did here. By what? Changing what? Taking the power of this 72 and let it become what? The coefficient of the log. So I can do that for each of these log. Their power will now become their coefficient. And remember, this power is still outside. It's still going to multiply whatever outcome I get at this point. So this is as 1 over 3 into the power here, come and multiply 3 log 2. Remember, each of them is having what? Base 10. Because anytime you see a log that does not have a base, that is what shown, It simply means that that particular log is in what? The base 10. That is what it simply means. So plus the power of this one will come and attach itself and become the coefficient here. 2 log 3. Now, isn't this beautiful? Now, tell me. Isn't this beautiful? We've been able to work our way backward to get an expression that will help us to do the actual substitution that the question requires, and then be able to represent the log in terms of what? X and y. So now that I've gotten to this point, and I have 3 log 2 plus 2 log 3, I can now do substitution for this log 2 and what? Log 3, because it is already provided in the question. So since I have log 2, I can replace it with x. Since I have log 3, I can replace it with y. So you see the thinking process now, okay? So this is now the same thing as 1 over what? 3 into 3 log 2, replace it with x. 3x plus 2 log 3, replace it with y. 2y. Isn't this beautiful? Please, I need your comment. Isn't this beautiful? Isn't this interesting? What we have done so far. Breaking it down, like walking backward to arrive at this. So interesting. And so what can I do at this point? Well, simply use the power outside. This is the value outside. And what? Expand the bracket. So 1 over 3 will now go and multiply what? 3x. This is the same thing as 1 over 3 multiplied to 3x plus 1 over 3 multiplied to 2y. 3 goes on to cancel 3 here, because 1 over 3, 1/3 multiplied 3 is going to give you 1. Just 1 that is remaining. And 1 times x here will give you x. Plus 1 over 3 times 2 is going to give you what? 2/3. That is 2 over 3 what? Y. So, you see substitution. We have done substitution in logarithm. And the process is so interesting. How we came about all this and then arrived. Like I said at the beginning of solving this question, I told you that we are asked to do substitution. Replace this to be represented in terms of x and y. But the only information I was given is that x, anywhere I see log 2, I can replace it with x, and anywhere I see log 3, I can replace it with y. I'm just showing the thinking process, not just solving randomly, to show you how logically I thought about this logically and implemented some certain steps to work backward. Because that is why mathematics is so interesting. You can walk forward, arrive at an answer, and you can still walk backward to generate a different entirely different answer. That is the process. I want us to simplify 72 into 8 times 9 and reduce each of them, represent it in logarithm form. Everything I've been doing obeys the law of logarithm. I did not just manufacture this out of the blue. This particular aspect is quite what in the laws of logarithm. We say that if two things are multiplying, it is actually the addition multiplication law. If two things are multiplying, it's something as if you separate them, provided they have the same base. This can be represented, this and this are the same word, the same thing. So I have to represent it this way so I can solve for that. And this is where we've arrived. So basically, this is what substitution in logarithm is all about. This is it. So we're going to be going into the next aspect, which is what? The equation aspect of logarithm. Sabao, thank you so much. I appreciate you. Thank you, I appreciate you. So I'm going to clean this up now, and then we enter equation involving logarithm, or logarithm involving equation. Or I don't know if we should solve one more question under substitution to make sure that we have a good understanding of it. Maybe I think we can solve one more question under substitution in logarithm. Let me find a question that we can solve under this, and then we proceed. If not, we will just go on. Let me find a question. One moment. Okay, I think I have one. One more question under substitution in logarithm. Let's do that. So if log 2 base 10 is equals to, if it's equals to 0.3010, and log 3 base 10 is equals to 0.4771. Evaluate, the question is now evaluate log 4.5 base 10. Now look at it, this is another substitution because how? We are to substitute anywhere we see log 2 base 10, we can replace it with 0.3010, and anywhere we see log 3 base 10, we can represent it with what? 0.4771. So it's substitution type of problem in logarithm. So what can we do? Remember, the key idea is anytime you're seeing substitution problem, first thing you need to do is to work backward, especially with respect to logarithm. You're working backward. So the log that we're given is log 4.5 base 10. This is the log that we are given. So we have to work backward. How can we work backward? We know that this 4.5, if I change it to fraction, it's same thing as what? 45 over 10. Well, that's not really much, but it's something that we can actually do to actually continue with our solution. So if we go on to do that, this is going to give us log of 45 over 10 base 10. It's not really a huge thing that we have done, but it's going to get us closer to the simplification that we need to do here. Well, what can we do here? Well, I know that I can simplify this 45 over 10 because it is not in its lowest term. I can go ahead and simplify it. So if I use 5 to divide 45, it's going to give me 9. If I use 5 to divide 10, it's going to give me 2. So this is something I'm saying what? Log 9 over 2 base 10. Log 9 over 2 base 10. Well, since we're working backward and we're having division here, well, I know that under the subtraction quotient law of logarithm, if I have log a base b minus log c base b, is same thing as what? Since the logs, the base are the same, pick one of the base and then divide the log. So if that is the case, this form is already in this form. I now want to put this form in this form because according to the law of logarithm, both of them mean the same thing. And putting it in this form will help me in actualizing my dream. What is my dream? My dream is to represent this expression in terms of log 3 and what? Log 2 base 10. That is my dream. Okay? So let's go on and do that now. So representing this in terms of this original expression simply means that we're going to have log base of 10 and then 9 will come first. This division here will now what? Change to what? Subtraction. Minus same log to the base of what? 10 and then 2. This and this are the same thing according to the laws of logarithm. So how to put it this way? Because putting it this way will help us in our what? Actualizing our dream. So in this form now, we are getting closer. At least log 2 base 10, that one is sure. We can replace it here. But log 9 base 10, well, there's no avenue, there's no provision for log 9. So I need to do a bit of simplification. How? I know that 3 squared is same thing as 9. So I can replace this 9 with 3 squared. So this is same thing as what? Let me continue here. Log of 3 squared base 10 minus what? Log 2 base 10. And then I can go on and apply the power law of logarithm. Take the power and what? It becomes the coefficient of the log here. So this is same thing as what? 2 log 3 base 10 minus what? Log 2 base 10. Now at this point, I can now do my substitution because I've represented it in such a way that I can replace what? Log 2 base 10 to what? This value here, which is 0.3010, and I can equally replace log 3 base 10 to be 0.4771. So doing that here, this is now going to be 2 multiply what is the equivalent of log 3 base 10. This is it, 0.4771 minus what is the equivalent of log 2 base 10. It's equal to what? 0.3010. So let's go and multiply these together. If I multiply this together, it's going to give me 0.954 642 minus 0.3010. So we can actually go and simplify this. If I simplify this now, it's going to give me 0.6352. Okay, 6532. 6532. Ha! So the substitution helps us to simplify this given log, and this is where we arrive at. Yay! So with this now, I'm sure that you know how to do substitution in logarithm. I've simplified the process. It's more about working backward and applying the laws that you know. Okay, that's what we did here. So the key point that I will mention in this simplification process is at this point where I knew that if I have anything, log anything that is divided by another thing to a given base, that I can represent it in this way, and nothing, it will be as though I've not done anything wrong. That's the key point or the highlight of this solution. So that's basically it. Now we're going to be entering into equation involving logarithm, and our focus today for today's class is to be linear equation. On Monday, which is when I'll be live again by 4 p.m. Nigerian time, West African time, we'll talk about simultaneous equation in logarithm, and finally, if time allows us, we'll talk about quadratic equation in logarithm. So I'm going to clean this up. Please take a screenshot if you can. This solution is so interesting. I love what I'm seeing here and what we've been able to achieve. Kudos to us. So let's go. So at this point now, we're going into equations in logarithm. And just like I did when we talked about indices involving equation, that is equations in indices, I pointed out some key things that you must see before you can know that this particular expression is an equation. In mathematics, there are three basic things that you must know that forms or that every equation must have. For something to be an equation in mathematics, it must have this basic ingredient. The first thing, it must have an equality sign. You must have an equality sign. There is no equation without an equality sign. Okay? And then secondly, there must be a left-hand side and what? Right-hand side separated by the equality sign. By the equality sign. So that is it. There must be a left side of the expression and the right side of the expression or equation, and each of them, both of them, is separated by the equality sign that is placed in between them. And then 3. This is where, well, me personally, I used to believe that every equation must involve a variable, something that you are looking for. For example, x minus 2 equals to 10. This is an equation because we are looking for the value of x here, which is a variable that will satisfy that once we plug the value of this x here and subtract 2 from here, it should give us 10. But this is just an algebraic aspect. This has to do with algebra. A mathematical equation is actually what is known as a true statement. Something that is true. So for example, 2 plus 3 equals to 5. This is an equation. Yes, because it's a true statement. Because this is simply trying to tell us that 2 plus 3 is the same thing as what? 5. So, major thing, equality sign, left-hand hand and right-hand side, and then it's not limited to variable expression, that is algebraic expression. These are not the only expressions that make up an equation. This is a mathematical equation and it's a true statement. It's a true statement because it's a mathematical equation. So that is basically it. Now, with that in mind, we go on to explore to see how equations involving logarithm comes up, how we can be able to note them. So we'll solve a couple of examples before we call it a day. So what are we going to solve? Okay, given that log 256 base x equals to 2, find the value of x. Well, this is up to a good start because this particular expression here, which you have log 256 base x equals to 2. Now, to solve this particular equation, all we need to do is apply the basic law of logarithm, the basic ideology behind logarithm, which I usually state. What is the basic ideology? If I have log a base b is equals to what? C. What logarithm is trying to tell us? Remember that logarithm, just like indices, is just another way of expressing what? Expressing numbers. That's what it simply means. You're expressing numbers in a certain way. For indices, you're expressing numbers in terms of a base and a power. But for logarithm now, what you're seeking to do is, based on the definition of logarithm, that the logarithm of any number to its base is the value of the power that the base has to be raised to give you the logarithm. So that means that a, which is the logarithm, is same as what? B, which is the base raised to the power of c. Yes, that's what that is what it simply means. So if I have a number and I know the base, what I'm looking for is the power. So it's like, if you look at it, it's more like an equation because at any point in time, if one is missing, you have to go and find it. That's what we're looking for here. So the base is what is missing here. So what I'm trying to find here is what value of the base will I raise to the power of 2 that will give me 256. That's the basic ideology. So let's go and implement that here. So this implies that the base here raised to the power of 2 is same thing as what? 256. This is what it implies. So if the base raised to the power of 2 equals to 256, what are we supposed to do here? Well, to find x now, which is the base, we can decide to square root both sides. Yes. Or find a number that will raise to 2. That, like, there are different couple of ways you can do that. So what we can simply do is what? To square root both sides. Square root both sides. And if you square root both sides, because this is a quadratic expression, it's not going to be the square root of what? X squared equals to plus and minus value of the square root of what? 256. Yeah, because once you are having a quadratic equation, two values will satisfy the given expression. So this square cancel this square root, so that our x is equals to what? The square root plus and minus what value of the square root of what? 256. And the square root of 256, I think it should be 16. 16, 2 times 6 times 6, 36, 6 times 1, 9, 6, and what? 1. Yeah, I think it's 16. So this is same thing as what? Plus and minus what? 16. That is to say that what? X is same thing as what? Plus 16. Or x is same thing as what? Minus 16. But for the purpose of logarithm, which we are discussing, it is right for us to pick positive. Positive what? Positive 16. Because having a negative base, it further complicates the solution. So it's mostly a positive base that we end up having. We don't really work with a negative base, or maybe I've not really come across where we have a negative base, or we can apply change of base system. That also work, but what you are used to is mostly a positive base. But because of the reason why I had to put a plus and minus sign is because both the positive and negative aspect of them, this given solution here will still give us what? 256. If I do minus 16 squared minus 16 all squared, it will still give me 256. So that's just the basic it. So this is the basic solution to this given what? Equation. So here we solve an equation involving what? Logarithm. So I'm going to clean it up and solve another equation. Let's solve another. Okay, if this particular one is actually related to the first one, given that log 256 base x equals to 2, find log x base 1 over 8. Yeah, I think that's, yes, this is what we have. Given that log 256 base x equals to what? 2. Find log x base 1 over 8. So solution. I think we've actually solved this before, so we can just simply go and what? Solve it again. We have log 256 base x equals to what? 2. Implying that according to the law of logarithm, we say that log a base b equals to c. It simply means that your b is same thing as, that your a is same thing as what? B raised to the power of c. So if I apply that here, it's same thing as saying that Now 256 is equal to x raised to the power of 2. And this 256 is something as well 16 squared equals to x raised to the power of 2. So if the powers are the same, it simply means that the base will still be the same. So x is something as what? 16. So I found the value of x to be what? 16. That is not the question. This is the real question. Find log s base 1 over 8. So we're having now log x base 1 over 8 is something as what? Log 16 base what? 1 over 8. This is now where we're going to be what? Solving. So what do we do here? This is the thinking process now. Let us evaluate this as mathematicians. Let us look at it with the eye of a mathematician. So if I have this expression, both the log and the base, they are dissimilar. So there's no way, they are not related. But there are a couple of things that I could do. I'm going to use two methods to solve this, to show you that we can use one of the methods that I mentioned when we were discussing about change of base at the beginning of this class. We're going to be applying that method here. Yeah, we're going to be applying it. So first thing first, I can decide to do applying change of base. Applying change of base system. So if I'm applying change of base system, it's now left for me to choose the base that I want to attach to it. So let me choose base 10. Changing both to base 10. So this is just to show what I'm doing here at this point. So if I change to base 10, remember, if you're changing base, if you're changing a given logarithmic expression, if you're changing the base of it, it simply means that it's going to now become log of 16 base 10 divided by what? Log of 1 over 8 base 10. This is what it means, and not subtraction. I made that mistake at the beginning of the class, so I've corrected it at the beginning of this particular live section, and I hope you've taken note of that. So we've changed the base now, and by changing the base, the original log becomes the numerator, and the original base becomes what? The denominator, all now having the same base. So we can now go ahead and simplify here. Well, 16 is something as 2 raised to the power of 4. And the 1 over 8 is something as what? 1 over 2 raised to the power of 3. Because 2 raised to the power of 3 is something as what? 8. Which I can revert to become 2 raised to the power of negative 3. So this and this mean the same thing. 1 over 8 is something as what? 2 to the power of what? Negative 3. Wait, you don't believe me? You don't believe me? If I have 2 to the power of negative 3, according to the law of negativity, this is something as 1 over what? 2 to the power of 3. And that will give me 1 over 2, 1 over 8. 2 to the power of 3 is 2 times 2 times 2. So it's something as 1 over 8. So basically, this is something as log to the base of 10, 2 raised to the power of 4, replacing 16, divided by what? Log to the power of what? 2 to the power of negative 3, replacing 1 over 8 base 10. So I just apply the basic power law of logarithm. Take the powers and let it become the coefficient of the log. So it becomes, this comes here, this comes here. 4 log 2 base 10 all over minus 3 log 2 base 10. So you see log 2 base 10 is common to both the numerator and the denominator. So they cancel out. So this is simple as what? Minus 4 over 3. Or 1 whole number, or minus 1 whole number, 1 over 3. This is what you have. So we apply change of base system, and this is where we arrived at. Now, take note of this, and we're going to use the shortcut that I mentioned before now to explain this or to solve this particular question. Let's use that shortcut and solve this particular question instead of going through this route. So take note of this, take note of what I did here. I'm going to now use the shortcut. What is the shortcut? The shortcut is simply this. If I have an expression, it is common that if I have an expression, maybe log a raised to the power of b base c, the power of the log will come and become the coefficient, b log what? A base c. But what if it's the base that has a power, which is if I have log a base b raised to the power of c. Now, this is going to be the inverse, because if the power multiplies the log, it's something as the power over 1. So if the base is one that is having a power, it's not going to be the reverse or reciprocal, multiplying what? The log. The reciprocal of the power of the base, multiplying the log. This is something as what? 1 over c, which is the power of the what? The base. But now reciprocal. Log what? A base what? B. So this is what it simply means. Now, where is that getting us to? Remember, let's use it and apply here and see where that will get us to. Don't rush. Let's apply it here. So this is not going to be log of 16. Let me replace this 16 with 2 raised to the power of 4. And then 1 over 8, we already solved it before now to be 2 raised to the power of negative 3. That's what we have. So if the log is the one having power, it will multiply a coefficient. If the base is one having power, it will multiply, but it's going to be the reciprocal. So this is something as saying 4, which is the reciprocal of the power of the log, multiplied to 1 over negative 3, which is the reciprocal of the base. Because if the base has power, then it's going to now multiply what? The log, become the coefficient of the log, but it's going to be the reciprocal, 1 over. So if the power here is negative 3, it's not going to be 1 over negative 3. That is what you have here. This 4 is for this word log, which is normal. Then this negative 3, this 1 over negative 3 is what? The reciprocal of what? The base. Then multiply to what? Log 2 base 2. So you strip both the log and the base of their power, and that's how you do it. Now, once you come to this point, it's not going to be 4 multiplying my 1 over minus 3 times log of anything to its base is going to give you what? 1. So what are we getting here? At this point now, all of them have a denominator of 1. This is same as saying 4 times 1 times 4. Then 1 times minus 3 times 1 is going to give us negative 3. Which is same as bringing the negative out, negative 4 over 3, or negative 1 whole number 1 over 3. So you see, you choose the method that works for you. If you're so comfortable with this, you can use it. If you can also apply change your base system, you can. So this is what I do here. Break it down. I've broken it down for you. So you choose. I've served you 2 different approaches. You go about solving this. The key thing to know here is if you have just an expression that has the base having a power, then you can take the power of the base and it becomes the reciprocal 1 over multiplying or becoming the coefficient of the log. Take note of that. It's going to save you a lot of stress. So at this point now, we'll solve one more question. 1 minute. Okay, I think I have one more question for us to solve. Yes, let's solve one more question before we call it a day. And the next time we'll meet, we'll start with one question on equation, involving the linear equation in logarithm before we go into the simultaneous and quadratic equations. I hope this class is interesting to you because, oh my god, it's so interesting. So let's solve one more question before we call it a day. Given that 8 raised to the power of y over 4 equals to log 16 base 2, find the value of y. Yes, find the value of y. How do you propose we start solving this? No, what do we do? Well, don't rush. Look at a given expression, what you are given, and see if there are some basic things you can do, because any complex thing you think that is complex has some basic things that will be applied. You're not just going to give me an answer for this, no. But the thought process of what you did on how you simplify some things is what makes math so beautiful and so interesting. That is the logical aspect of math. So this is simple as saying 8 raised to the power of y over 4 equals to, I can replace 16 to be 2 raised to the power of 4. 2 raised to the power of 4 is simple as 16. So this is simple as log 2 to the power of 4 is what? 2. And then here I can apply what? I can apply the power law of logarithm, which if the log has power, it comes and becomes the coefficient of the log here. So 8 raised to the power of y over 4 equals to 4 log 2 base 2. And any log to its what? Base. Any log that has the same value as its base equal to 1. It is proving. 8 raised to the power of what? Y over 4 equals to 4 multiplying what? 1. So 8 raised to the power of y over 4 equals to 4. So I've done it now. So even if we've not gotten our y, I've done something. I've simplified at least the right hand side. So we've actually done something. So clap for yourself. You've done something really good. So at this point now, we do some basic work. We do some readjustment. 8 here is something as 2 to the power of 3. 4 here, 4 is something as 2 squared. So we are trying to rearrange both the left hand side and the right hand side base to have the same base. There's a reason why we're doing that. The same base raised to a certain power. So replacing 8 here with 2 to the power of 3 is simple as 2 to the power of 3. That's the value of 8. And they have the outermost power, which is y over 4. Equals to replacing 4 here with 2 squared. and then employ the power law of indices, which if you have two powers, one inside and one outside, use the power inside multiply the power outside. So this is same as saying 2 to the power of 3 multiply y over 4 equals to the 2 to the power of 2. So this is now going to give us 2 to the power of 3y over 4 equals to 2 squared. Now, according to the laws of indices, when you're having laws of indices, if the basis of the expression on the left and the right hand side are the same, it simply means that what their power is same thing. So since the bases are the same, it simply means that 3y over 4 is equal to 2. And then we'll go on to simplify this. So how do you simplify it? You cross and multiply. 3y is equal to 4 times 2 is going to give us what? 8. And if you don't know how to cross and multiply, this 2 by default has a denominator of 1. 3 times y, 3y, 4 times 2, 8. And then you divide both sides by the coefficient of y, which is what? 3. Y will now be equal to what? 8 over 3. So the value of y that will satisfy this given expression that we had here originally is equal to what? 8 over 3. So your assignment now, what I want you to do for me, I'll be in the comment section waiting for you. Please make sure that you do it, okay? Come over here, replace this y with 8 over 3, simplify it, and see if you're going to get the same value as the value of log 16 base 2, which gave us 4. See that after you substituted y equals to what? 8 over 3, and simplify this left hand side, do you get 4? That is what I want you to do. So day 9 of going live on YouTube has been successfully achieved. Thank you so much, guys, for sticking with me here. Thank you so much. I appreciate you, and I hope that you learned a thing or two from this live section. We're going to continue again on Monday. Remember, I go live on Mondays, Wednesdays, and Fridays. What time? 4 p.m. Nigerian time for now. Okay. If there's need for adjustment, I'll communicate with you guys. Always check out my YouTube story too and post. Yeah, because I'll be posting more information on there. Thank you so much. And also, if you like to reach out, you can actually reach out to me on TikTok. Is my username Uncle Sam 160, and then you can reach me on Facebook and Instagram with the name exactly the name of this my YouTube channel, which is Uncle Sam Online Tutorial. So if you also need help with some assignment or you need some private lessons on math, you can also message me on WhatsApp. You can also message me on WhatsApp with this number so that we can bring it up to a level that you want to be. Thank you so much for coming to this live class. I appreciate every one of you. Thank you. Thank you. Gracias. Gracias. Thank you. See you on Monday.